Hi, and welcome to a very brief introduction to the physics that underlie X-ray fluorescence. We're going to focus on applications in archaeology, geology, and art conservation, not because they're inherently better than others, though some of us may have a bias in that regard, but rather because they present a unique challenge. Typically, X-ray fluorescence involves the analysis of homogeneous samples. This makes it relatively straightforward to create a quantification procedure. However, for pigments in a painting, inclusions in a rock, or ancient paint on ceramics, the answer is not so straightforward. It's a much more heterogeneous material. But if we learn a little more about the physics that underlie X-ray fluorescence, we'll understand how to handle these challenges and, as an added plus, learn more because of them. We're going to begin with the physics of color itself. Color, like X-ray fluorescence, is itself fundamentally a fluorescence process. First, a photon is emitted from a source. Now take a second and look at the photons around you. You're probably watching this in either a computer or a television set. In this case, photons are coming from an LED light or a cathode ray tube. If you're sitting in a room with a window, you may be seeing light coming from the sun. Or if it's night, you may be having light come from fluorescent bulbs around you. What's important to remember is that the source of photons determines the colors that you are able to see. For example, the sun emits photons in a range of infrared to ultraviolet. This is why it's hot, and this is why you can get a sunburn if you're exposed to too much of it. This is not the problem with fluorescent lights because they have a much narrower range. They simply go from red to violet, no infrared and no ultraviolet. When we talk about LED lights or cathode tubes, very similar processes underlie them as well. Now imagine for a moment you take a fluorescent light and wrap translucent red paper around it. A color is going to be very different under these lights. You may not see shades of green or violet or blue. This is because you've changed the photon source, you're changing the type of colors that you're able to see. If you remember, a while back, we used to have incandescent bulbs that were much more common. The problem with these bulbs is that they were drastically inefficient. They were inefficient because most of the photons produced via this process were, in and of itself, just infrared. So we had more infrared than actual visible light photons. If you think of it as a bell curve, visible light photons only fit on a portion of the right edge of that bell curve. And that's why they also had sort of an orangish yellowish hue. Again, because a lot of the energy was produced, the energy source itself was producing a lot of infrared. Now the way sources work is very unique. For example, a fluorescent bulb, you have electrons pouring in from a hot wire on one end, and then they come streaming towards a positively charged anode at another. Because electrons themselves have a negative charge, they're very attracted to this positive anode. However, oftentimes to create light, we insert mercury vapor in these bulbs. Mercury strikes the electrons, and the electrons enter an excited state, producing a range of photons from 1.7 to 3.2 electron volts. Now, this is an important process to consider because, again, every bulb can be a little different, can produce a slightly different energy. The only light source in our lives that's completely 100% consistent is the sun. This is why art conservators typically work in very large windowed rooms, because the light coming from the sun will be the same in Brazil as it would be in New York, as it would be in Antarctica. Now the photon, after leaving whichever source it comes from, interacts with molecules in a sample. Now, let's focus on a molecule. That means there's more than one atom and almost certainly more than one element. In this case, the photon is interacting with the outer electron structure of these objects. Think, for example, if you're pulling out a steak that's been in your refrigerator for about 2 weeks. If it's green, you probably wouldn't eat it. This is because the visible light photons in the kitchen are interacting with the meat and fluorescing green, indicating that there's a very different type of molecule than just the meat itself. You do molecular analysis with your brain and identify that this may not be something you want to eat, unless you may be a dog. Based on the properties of that molecule, the photon is either reflected back, scattered, or absorbed. In the case of our old meat, all photons for red, which we'd hope to see, have been absorbed by the very new molecules, and instead green is reflected back. Then we have a detector, which is our eyes. We typically have 3 cone cells to see this with. Typically, cone cells come in 3 flavors: red, green, and blue, just like a color printer. Red photons interact with red cone cells, green photons interact with green cone cells, etc. Now, it's important to remember any biological population has a lot of variation when it comes to cone cells. So, for example, men typically have a reputation of not seeing colors near as well as women. This is largely because men are a little bit deficient with one regard. If you think of a chromosome is always shaped as an X. If you take a female, she'll have two unique chromosomes, an X chromosome and another X chromosome. This determines her sex. A male has an X chromosome and unfortunately gets a broken Y substitute for the other X, which means that any genes on that big X are the ones that the male has. There's no backup copies. This makes men much more likely to have fewer cone cells and go bald at earlier stages in their lives. Now, women, on the other hand, with two X chromosomes, can occasionally see many more different colors than most other folks can, typically because they can have upwards of 4 cone cells in place of 3, giving them a much richer sense or much richer set of combinations. The important point being that when we discuss color, we have 3 sources of subjectivity. The first source of subjectivity is our source. The second is the object that photon interacts with, and the third is the detector. If we can keep the source constant and the detector constant, then all variation will be driven by the sample you have. This point is very critical, because if we do not use the proper parameters, we can't replicate data. So in other words, if you take your tracer, analyze an object, and see key trace elements, change parameters, analyze another object, and try to compare the 2 results, you won't get meaningful information, because a great deal of the variation will be driven by changes in your photon source. But coming back to color fluorescence, we can think of red as around 1 electron volt. It's a little higher, but for the purposes of analogy. Violet is around 3 electron volts. And then we can produce a graph with photon intensity on the y-axis and photon energy on the x-axis. You can think of red as a big old bell curve right around 1 electron volt of energy. If we have blue, that bell curve shifts. This is what each of our cone cells see, and then our brain does the hard work of overlapping all this information. Let's take a look now at a ceramic, black on red ceramic, typical of the classical period in ancient Greece. Now, when we have black, all photons are absorbed. In orange, around 1 electron volts of photons are reflected back at our eyes. Now, the 2 colors you see here come from 2 different combinations of 2 distinct elements. Can you guess which one? Think about your bike that you may have had when you were a kid. The metal looked a gorgeous gray or black when you first got it, but over time it slowly became more and more orange. That's because the iron that made the black color slowly oxidized, changing the outer electron structure and creating a surface for low energy photons to bounce back instead of all photons being absorbed. This gives it that orangish red color. Here, classical Greek vases, typically speaking, they fire in a reduced environment with an extremely iron-rich slip. They can then scrape away the outer surface to reveal an orangish, yellowish, and red texture underneath. So thus, what you're looking at is not a painted piece of pottery, strictly speaking, but rather a carving that elegantly uses this physical phenomenon of iron oxidization. If you, as you can guess, black on red pottery and red on black pottery have more to do with the way the pot is fired than with the ingredients. Now, this is important because if you happen to analyze one of these ceramics and you see lead paint or titanium, I have terrible news. It may not be original. Now, with this idea of color, let's look at a painting and think of it as a map of energy coming back into our eyes. Our reddish-orange hues in the sky here are around 1 electron volt. The bright yellow is a little higher energy, around 2 electron volts. Green is a little higher still. White is reflected back. Black is absorbed. This creates an energy map. Note that the transitions here are very, very, very smooth. This is in contrast to this Van Gogh painting. As you notice, it's much higher energy, that your eyes perceive that as blue. But it doesn't just come down to that. The texture is different. It's much more heterogeneous. As a consequence, you can use energy information not only to decipher what the molecules present are, but how they are distributed. The same rules also apply for X-ray fluorescence. So a heterogeneous sample contains much more information than may first meet the eye. We can also use X-ray fluorescence for some pretty cool techniques. For example, take this Vincent van Gogh painting patch of grass. Like the one before, it uses a lot of high energy photons. These are a little lower in energy and again, non-uniformly distributed. When folks were using a synchrotron X-ray source to analyze this painting, they noticed a pretty high concentration of antimony. This is typically associated with white pigments in paintings. They then looked at the distribution of antimony, and this is what they saw. That's right, there was an entirely different painting completely underneath leaves of grass. This is because Van Gogh either didn't like this painting or had a change of relations with the subject and painted over it. This happens quite often. In fact, you'd be surprised how many different paintings have entirely different underlayers. But in this case, we can use X-ray fluorescence to see the painting underneath. This is because it uses higher energy photons, and higher energy photons penetrate deeper. We'll discuss just how deeply a little more later. Now that we have a firmer foundation of how color fluorescence works, let's return to X-ray fluorescence. Well, in the most basic terms, it is a process in which, you guessed it, a photon is emitted from an X-ray source. This part is the same. Think back to our fluorescent light bulb. We had electrons pouring in from a wire, attracted to a positive anode, and striking mercury vapor. This caused excitation in the photons, and we saw visible light as a process. Well, for X-ray fluorescence, we send higher energy electrons into a bulb, and in place of mercury, we typically use rhodium. Though you can also use molybdenum, chrome, silver, and other materials as an X-ray target. This excites photons and produces a bell curve that, instead of stretching from 1 to 3 electron volts, stretches from 1,000 to 40,000 electron volts. And these are the energies at which atoms fluoresce. And this interaction with atoms is the key difference between color fluorescence and X-ray fluorescence. With color fluorescence, you're interacting with the outer electron shells of molecules. With X-ray fluorescence, you're analyzing the fluorescence of internal electron orbits. As a consequence, we get atomic information, not molecular information. And I cannot stress this enough, atomic information. If you have an XRF device that is giving you numbers of oxygen, for example, that's a molecule. You do not see the oxidized state. Iron pyrite, hematite, and the two different states of iron oxide will fluoresce identical to each other. It's not a function of the molecule, it's a function of the physical numbers of atoms present for that given element. So if you do see results that report as oxides, take them extremely critically. There is no actual verification using X-ray fluorescence that a sample is an oxide. Now, what typically happens is an electron is knocked out of the inner shell of a given atom. And with that vacancy, you have an electron fall down to replace it. And this releases the photon characteristic for that atom. We'll discuss this process in a little greater depth just a little later. And then finally, just like your eyes, we have a detector to pick up these characteristic fluorescent energies. So the process of X-ray fluorescence is very close to the process of color fluorescence, for which you are familiar with in your day-to-day life. If we return to our first painting, we can use X-ray fluorescence to identify what pigments are used to make them. So for example, our bright reds are mercury and sulfur, or mercury sulfide. In impure concentrations, it's called cinnabar, and more pure concentrations, it's called vermilion. And it's a very traditional red used. It's also a source of a lot of mercury poisoning for unfortunate painters, such as Van Gogh. The yellow indicates either lead yellow or chrome yellow. Both are distinct possibilities. Now, it's important to note the use of chrome yellow can fix a painting in time. If you have a painting that's supposed to be very old, but you see chrome yellow, you may need to rethink that assumption. However, lead yellow may be much more common at older ages. Copper can typically be the representation of malachite, which is essentially iron ore that's been ground up to preserve sort of the oxidized copper green look. Lead white is very often used, and then our black here has both calcium and strontium. This would indicate it's bone black. Just for fun, if you look at a periodic table, look for strontium. Its elemental symbol is SR. You'll notice it's just below calcium. They have the same outer electron structure, and as a consequence, they tend to fraction together whenever any kind of chemical reaction takes place. So your bones, your teeth, which are primarily made of apatite, calcium phosphate, you'll have a large quantity of strontium present as well, just because it's hitchhiking along with the chemical selection process that goes for calcium. Now, we've been talking an awful lot about these things called photons. We should review exactly what they are. What is a photon? I'll give you a second to think of this. No answer? That's normal. If you do have an answer, you can write to the committee in Stockholm, because nobody exactly knows what a photon is. We do know a few of its more important properties, though. The technical definition would be discrete packets of electromagnetic radiation. Think back to when we were discussing color fluorescence. Red was around 1.7 electron volts, while blue was around 3 electron volts. In this case, the energy of the photon is essentially exactly what the photon itself is. It is a discrete packet of electromagnetic radiation. So that property of having different energies served in quantum bits is about as good a definition as any for what a photon is, at least at this date. Who knows what physicists in the future will be able to determine about photons. They carry force. Thus, when your eyes pick up, those cone cells pick up those photons, you start a little bit of energy is transferred to help mitigate that reaction. Plants use this same process not to see, but rather for photosynthesis. In fact, you yourself are entirely dependent upon upon photosynthesis, because presumably you eat either plants or animals. Because of this, you're fundamentally taking at least a portion of your body's energy, a large portion, from the sun indirectly. And this is because they carry force, and with force comes energy. Sometimes photons have the characteristics of a wave, sometimes a particle, and they are neither. And I must stress, they really are neither. I know lots of instrumentation reports results in wavelength, but it's important to remember these are models we have for the way photons interact. We don't exactly know how they are. And the wavelength model can only take you so far. This is one of the reasons why you typically see electron volts reported whenever you see characteristic K alpha or L alpha peaks of elemental fluorescence. One way to think through this process is think about Einstein's famous equation, E equals mc squared. E being energy, m being mass, and c squared being the speed of light. Now, have you ever thought, why didn't they use time or space as the constant? Presumably a meter is a meter, right? Unfortunately, the answer is no. It depends on the velocity you're moving at. For example, imagine you have an identical twin sitting next to you, someone with the exact same features, experiences, emotions as you, a perfect double, a clone. You hop into a spaceship, and you travel at 99.99% the speed of light, just racing towards the stars. You go for exactly 1 year, while your twin/clone remains on Earth taking care of day-to-day tasks that you would have taken care of otherwise. After about a year, you realize there's no Facebook or Reddit in space, and so you turn that spaceship right around and zoom to Earth. Again, at 99.99% the speed of light. When you arrive on Earth, are you going to see your clone 2 years older, just like you? Or will your clone be earlier, older, younger? The answer is you may not see your clone at all. He or she may have long since passed away, along with the civilization you counted yourself as a proud member of. Because as you go faster and faster, the experience of something traveling at the time experience of something traveling at a slow velocity will lengthen. And so 2 years for you, depending on the velocity, can be 50,000 years for another. So that's why Einstein didn't use time or space as constants. In fact, if you go ahead and get up and walk from one side of the room to the other, you'll notice that as you walk, you're crossing time, you're also crossing space. Unfortunately, according to what we know of physics, you're not allowed to cross that room without also crossing time. Think of a long car trip. How often do you tell someone that you need to drive 2 hours in this direction to get to said place? If someone asks you how long of a drive is at home, you may say 15 minutes. This is because you're recognizing the unique relationship between time and space. This is why they form the time-space continuum. You can't cross one without crossing the other. Now, there is one particle that is massless, and that is the photon. Because the photon is massless, it doesn't have the same limitation, and it can travel at, you guessed it, the speed of light. The speed of light is, to some physicists, the speed at which you travel if you lack mass. Once you gain mass, time and space unfold before you. So, and the way to think about this is going back to our spaceship example. You were traveling at 99.99% the speed of light, and boy, did your time experience speed up relative to an observer on Earth. If you went at the maximum velocity possible, the speed of light, presumably time would hit infinity, and thus you would be all time and no time at the same time. And distance itself would shorten so that there is no real experience of distance. You are anywhere, everywhere, and nowhere all at the same time. So this is why we don't exactly know what a photon is. These interactions are awfully strange, and it's a pretty strange world. I encourage you to read a lot more up on photon physics. However, returning back to why it's neither a particle or a particle would presume it has a defined area in time and space, which light does not respect. To have a wave, you must also have a wavelength. And that length aspect is once again trying to articulate a photon's experience in time and space. We can build excellent mathematical models using these two assumptions, but it's important to remember they are assumptions. The quote I often use, trying to bring me down to earth and humble myself when it comes down to understanding physics and science, is that all models are wrong, some are useful. The wavelength and particle properties of light are exceedingly useful, but usefulness does not imply correctness. So once again, photons, no mass. They have electromagnetic energy. In fact, some could argue that's about all we know that photons have. And they have a bit of momentum as well. Now, you have a lot of experience with all kinds of photons. Do you listen to the radio when you're driving to work in the car? Well, those are photons, pretty large photons with a large wavelength. Visible light is a narrow range, while infrared and ultraviolet are much larger. X-ray fluorescence simply interacts with a different area of wavelength as well. But as we discussed, a wavelength is not strictly speaking possible. It's just a model for understanding this. But these numbers are meaningful. So for example, a red photon with about 1.7 electron volts of energy will have about 700 nanometers wavelength. A blue photon with 3.0 electron volts will have around 400 nanometers. If you think about those nanometers as a diameter rather than a wavelength, you can actually get a better perspective of how photons work. Now again, we're talking about a diameter, we're using a different model of photons. Is it wrong? Absolutely. Pretty much all our ideas of photons are. But it doesn't mean it isn't useful. So imagine it's a nice sunny day and infrared photons interacting with your body. These infrared photons are taken in by your skin, and a few lower energy ones are radiated out. But the process is a heat transfer or a photon transfer. Goodbye. Let's say you listen to the radio. You know the size of your car antenna? It's about how large of the diameter of a radio photon as you're trying to interact with. Your cell phone actually operates with these larger photons as well. Think back to old TV systems that only had 3 channels. Do you remember the antennas? You had a short antenna, middle antenna, long antenna. And I bet that TV got through only 3 channels. Each channel, 1 bar. Each bar, a diameter for the photon or the wave frequency of the station it was interacting with. And remember how you had to turn it exactly perpendicular to where the signal was coming from? Again, you're just helping the diameter of a photon hit the diameter or the length of that antenna. Now, visible light are higher energy, higher energy, shorter wavelength, and that range of visible light interacts with the cone cells in your eyes, and voila, you have sight. Now, if we want to see something even smaller, we need to send in a higher energy photon, like X-rays, to bounce off the bones in your body and create a distinctive shadow. Again, the higher energy the photon, the smaller the diameter of interaction with objects that have dimensions in time and space, such as your bones and the cells in your body. Now, we've covered photons, we've covered some interesting ideas about photons. It's time to get to the basics of X-ray fluorescence and come to the atom. Now, this atom has 3 distinct orbitals pictured, K, L, and M. There's a couple different ways to remember this. I think of KLM, the Dutch Airways Company. You can also think of MLK, or Martin Luther King. Whichever is best for you. These electrons, negatively charged, surround a nucleus, which has both protons and neutrons. Protons have a positive charge, neutrons have no charge. They're pretty much irrelevant when it comes to X-ray fluorescence. Now, the proton exerts a positive attractive force, and this is greatly attractive to all the electrons around the atom, but they can't quite get into that nucleus for a variety of reasons, typically known as the strong and weak nuclear forces. Now, these electrons, though, do have favored spaces. Look back at this electron diagram. We've got 2 electrons in the K shell hanging out by the nucleus. This is pretty high value property. Just about every electron wants to be here for a couple of reasons. First, these electrons love to be as close to the nucleus as possible because it has a tremendously attractive force. Second, they want to be as far away as possible from all those other jerk electrons all around them. So as a consequence, there's a lot of competition in this atom for electron placement. You can think of it. Imagine the nucleus is the center of your city. The K shell are the houses around the center. The L shell are the suburbs. And the M shell are the boonies. Everyone wants to get to the center because it means a shorter commute to work. But unfortunately, there's only so much space there. And to make it even more interesting, each house has about the same price. So if an opening comes up in that K shell, boy, you had better get on that. Now, what we do is we send a photon in with a characteristic energy, diameter, wavelength, however you want to call it, that works exactly right for a given electron in a given orbital. And this photon and electron meet up and become the same essential thing. We now have a highly energized electron. Now, what's interesting is a lot of people wonder, why do photons only seem to interact with electrons? I mean, most of your experiences day to day, whether you're using X-ray fluorescence or color fluorescence, are fundamentally photon-electron interactions. Well, a way to understand a little bit of this, and it's only a hint, we really don't know, is that when you send a really high energy photon into the center of a nucleus, it needs to have about 1,220,000 electron volts of energy. It goes right through that nucleus. It's small enough to fit right through the spaces. So it's even able to skip past the strong and weak nuclear forces. However, this does not come at a cost. That photon is literally ripped apart, probably by the boson, by the gluons, and it becomes two different distinct particles, each with half the mass, about 511,000 electron volts. One is positively charged, one is negatively charged. The negatively charged particle we call an electron. The positively charged particle we call a positron, or antimatter, which is really interesting. And if you remember, or you may have heard of this, if matter and antimatter meet, what happens? They disappear in a burst of light. So electrons and photons have a pretty deep relationship. I don't think we've teased all the nuances out of it. But what we need to know for right now is that if you send the right photon in, it's going to meet up with the right electron, and magic's going to happen. You can almost think of it as a boy and a girl who are just perfect for each other, both living in their parents' basement. When they meet, they combine their incomes, they can now afford rent, and they get out of their parents' house, leaving a vacancy in that K orbital. Now, remember how I mentioned earlier how all those other electrons want desperately to be in a more internal electron valence shell? All make a run for this brand new deluxe opening near the center of our atomic city. They start moving around, and finally one is able to cross that energy barrier and snap into place. And once it does so, it drops from one energy level to another. Now, one way I like to think about photons is they are a lot like a currency for electrons. The way to think about this is actually Apple. I'm a big Apple fan. In fact, I'm recording this on a Mac. As a consequence, whenever Apple releases a new project, I typically pull out my wallet and say, take my money. My money are the photons, and I am an electron who's awfully excited and ready to send off stuff and to jump down to a lower energy state, which would be an emptier wallet, but hopefully with an iPad or an iPhone. Now, in this case, the photons are the currency of energy. When that electron drops down into a lower energy state, well, that energy has to go somewhere, and it's released in, guess what form? Another photon. As it jumps down, we have a new photon come out, and this photon is the energy difference between the L and the K shell. Now, if you think about it, what is determining that payload, that number, that energy state? It's the number of protons in the nucleus. More protons, more attractive force, a higher energy state to drop from one to the other. Now, with more protons, you get a new element. If you have more neutrons, you have a new isotope. And if you have more electrons, you have an ion. So it's important to remember another proton, a different difference between two orbital energy states around that atom, and thus a different product photon coming from X-ray fluorescence. And so this is the fundamental reason why X-ray fluorescence is so useful for identifying individual elements in a sample. This is also why X-ray fluorescence is absolutely, utterly useless towards validating whether an element is in one molecule or another, because the outer electron orbitals don't matter in this transition. It's only the internal electronic structure that we interact with. Now, the atom is nice and happy, a little more stable. A couple points of terminology here. Because this is electron, photon, essentially subatomic particle interactions, we're dealing with quantum mechanics, not the laws of physics you and I use every day. So as a consequence, we're dealing with probabilities, not certainties. So we can only say if something is more or less probable. We can't actually predict it very well. However, at least for individual cases, when you have hundreds of thousands or millions of cases, then the probabilities emerge quite regularly, and you'll see this in your spectrum when you take data. When an electron jumps from the L to the K shell, which is the more likely event to occur, it occurs about 6 out of every 7 times. We call that a K alpha peak. However, 1 out of 7 times, it is going to come from the M shell. We call that a K beta peak. Every characteristic fluorescence is going to be a little different. So, for example, the L to K, while more common, is a lower energy transition. There's only one shell difference between the two. However, the M has to jump over another orbital. So as a consequence, while it's going to be about 1/7 the size of the K alpha peak, it's also going to be occurring at a higher energy, or further along the x-axis. Now that's why every in the periodic table, each element has a different fluorescence energy. As you add protons, you add attractive force, and thus you add the energy needed to shake one electron to another energy state. Our spectrum typically look like what you see here. If you look to the right, around 6.4 keV, you'll see the characteristic K alpha peak for iron. If you look a little further to the right, you'll see the K beta peak. You'll notice that the higher K alpha peaks also result in a higher K beta peak. As long as your sample's on the surface and homogeneous, these guys are always going to be at the same ratio to one another. However, if you have layering or a different matrix you have to measure through, you're going to have a larger representation of the K beta peak relative to the K alpha. Looking further to the left, you see that red mountain range. Those are multiple characteristic peaks of barium. This is barium fluorescing from the in the L orbital. Because there's more electrons there, there's a lot of different possible electron-electron interactions. As a consequence, rather than getting 2 distinctive peaks, we get about 9. Though usually only 3 or 4 are going to be easily visible in the spectrum. And then, as you can tell, from the high concentration of silica to the far left, this is a silicate sample. Now, what's important to remember, if this is a silicate sample, do you know what element is the most common? This is going to be true for ceramics, obsidian, glass, and dirt, and all the rocks you see. You might say the most common element is silicon, but it's not. It's actually oxygen. About half the weight of that rock, if you hold it in your hand, is going to be coming from oxygen. In fact, you can think of all the other elements present, whether it's silicon, aluminum, sulfur, iron, calcium, as just being glue that's holding together a lot of oxygen. We can use this, of course, quantitatively to get a sense of relative weight percents for each of these elements. But the next thing to think about is that if we're measuring at different energies, we're also measuring at different differences of depth. So, for example, here is a mass attenuation curve for a typical silicate. This is glass, ceramic, obsidian, or Pyrex. I actually calculated this using only Pyrex, so this is a particularly optimistic view. Pyrex is silicon, but boron is also used. Boron, being a very light element, is going to result in a less dense ceramic. So all the depths here are the most optimistic outcome. Typically speaking, any rock or sand or soil sample you pick up is going to have a lower, though still roughly representative, measurement depth. We calculate this using the mass attenuation coefficient. If you look over, you'll see I over I0 equals E raised to negative mu over rho times X. I represents the energy of photon and coming back from your sample. I0 equals the energy of the percentage of that energy photon coming back. We're going to use 90. We're going to assume only 1% is coming back, about the maximum depthness we could possibly detect for each element. Negative mu over rho represents the attenuation of a given element in a given density. And then X represents the actual density of that object. So as you can see, the higher the density, the lower the depth of measurement. We can actually reduce this by assuming a 99% loss of photons for each given energy as depth in centimeters equaling 4.63 divided by the mass attenuation coefficient, or negative mu over rho, times the density. You can look for negative mu over rho values for given chemical formulas or for given materials on the National Institute of Standards and Technology's website, nist.gov. I would recommend Googling it, though, because it might be a little easier to navigate than that particular website. Now, if we look at the curve, on the x-axis we have energy, the same energy we saw earlier, ranging from 1 to 40,000 electron volts, or 1 to 40 kilo electron volts. And on the y-axis, we have penetration depth in centimeters, ranging from 0, the very surface, to 4 centimeters. Silica fluoresces at about 1.7 electron volts, so it's going to be on the far left near 0. It's going to be so shallow that you're really only measuring 20, 30 microns at best. As you go up in energy to iron, you start measuring a little deeper. As you measure up to 40 keV, you can pound through 4 centimeters of a given material. If we look at it with numbers, we can see that the different elements with their different energies of fluorescence and different depths of measurement. So look, for example, at oxygen. We don't see oxygen with X-ray fluorescence, but typically speaking, it is technically speaking fluorescing as long as you're sending in the right energy. In this case, we're sending in about 0.53. We're getting 0.53 keV in fluorescence for oxygen. Our analysis depth in centimeters is going to be 0.000001. So we're not measuring it that deep. If we go over to silica, at about 1.7 kiloelectron volts, we're measuring at 0.0027 centimeters, or 27 microns. Not that deep, really, if you think about it. If we go down to iron, which fluoresces at 6.4 keV, we're down to 0.03 centimeters, or a third of a millimeter. That's decently deep. Zirconium, which fluoresces at just under 16 keV, we're going to see 0.38 centimeters, or 3.8 millimeters deep. Now, this is important first because you're measuring each of these elements at a different depth. So even if, let's say you're measuring a sample that is pure iron oxide, let's say its first oxidization state, X-ray fluorescence still cannot tell you whether or not it's oxidized. Why is that? Well, you're measuring your iron at about 0.3 millimeters deep, but the oxygen is being measured less than a micron at the surface. So as a consequence, you can never really prove that oxygen is bound with iron, even with statistics, though they should roughly line up, but only roughly. This is pretty important in understanding how to handle variation. A lot of your samples may have different variation. So if you want to measure zirconium reliably, your sample is going to be at least as thick as you're seeing zirconium in the sample. Any thinner, and some of the variation in zirconium you get is going to be driven by the thickness of your sample, not the actual concentration. Remember, X-ray fluorescence is measuring atoms, not weight percent, not parts per million, purely atoms. The thicker the sample, the more atoms. The deeper the sample, the more of those atoms you happen to measure. Now let's return over to a different curve, this one for a lead glaze or a lead glass. On the x-axis, we have our energies, and on the y, we have our penetration depth. But instead of 0 to 4 centimeters, we have 0 to 0.04 centimeters. So thus, through lead glass, we're not even measuring half a millimeter, even at 40 keV. This is because lead has such a higher density that, remember our equation, depth equals 4.63 divided by the mass attenuation coefficient times density. As density in the denominator goes up, your predicted value goes down. And so thus, as a consequence, the density matters greatly. Now finally, to conclude, how do you handle all this variation? Well, there's 5 parameters for data collection. And if you keep everything the same, you can use a quantitative calibration, or you can analyze your data semi-quantitatively. You'll need to have the same energy in keV. That means if you're shooting a sample with 40 keV, that's great. Make sure all your other samples you're going to compare that data with are also shot with 40 keV. Remember, if you control your source, you're going to see the same thing. You'll want to measure with the same current. Current in this case can be thought of as the number of photons per second coming in. Just like current in a river can be articulated as how many water molecules are moving per second for a given unit of space. You'll also want to use the same filter. Filters change the light source quite distinctly. We'll discuss those in a later lecture. You'll also want to use the same time of analysis and, importantly, the same atmosphere. A sample measured on Earth where the atmosphere is primarily nitrogen and oxygen, will give a different spectra than a sample measured on Venus, which is about 95% carbon dioxide. This is because the density of the air itself is going to change the ease at which you see that spectrum. All these 5 parameters affect the source of light. Anyway, thank you once again for your attention. We'll have more videos for you soon. And if you have any questions, don't forget to email us. You can reach me at lee.drake@brooker-elemental.com. Thank you for your time, and bye-bye.